Okay, so this is a continuation of the previous lecture. So we have just seen that projective space is covered by n+1 copies of open sets which are isomorphic to affine n dimensional space. Now what I wanted to say is that from this the first thing that we should notice is that if you take any projective variety, a projective variety is an irreducible closed subset of projective space, then that projective variety, if I intersect with ui, I will get a projective variety and take its image, I will get a projective I will get an affine variety in an, okay, and therefore from this you will get that any projective variety is a finite union of affine varieties, okay. So that's so these are all corollaries of this construction. So these are all observations which are very important for us. Number one, the projective space itself is a union of all the ui's I equal to 0 to n, each ui isomorphic via phi to an. So you have this. 2, if x is a subset of Pn, then x is a union of from I equal to 0 to n x intersection ui. So any projective respectively quasi projective variety is covered by finitely many affine respectively quasi affine varieties, okay. And the most important thing is that any variety as therefore is a finite union of open subsets each isomorphic to an affine variety. Okay, so so for that if you take a Pn, or if you take a projective variety, it's very clear that by the first two remarks that it is certainly a finite union of affine varieties. The only case that one has to cover is the case of quasi projective or quasi affine varieties. Okay, so what I want to say is that if you take, first of all I want to say that if you take a quasi affine variety, that also can be covered by a finite union of affine varieties. Okay, so 3 any quasi affine variety is a finite union of affine varieties. Why is this so? Because you see, you take y inside some am, this is irreducible closed, which means that y is a closed subvariety of affine space, so it's y is an affine variety, and then in that you take a u non-empty open, then this u will be a quasi affine variety. By definition, a quasi affine variety is a non-empty open subset of an affine variety, and now y is z of P, where P is a prime ideal in the P inside the affine coordinate ring of this affine variety AM prime ideal. So it's a zero set of a prime ideal because it's a variety. Okay, it's an irreducible closed subset, so it corresponds to a prime ideal. It's a zero set of that prime ideal, and this of course anyway this ideal is in this, which is a polynomial ring in m variables, and it is by Hilbert's basis theorem, it is it's Noetherian. So the prime ideal P is also finitely generated, any ideal is finitely generated, so you can write, if you write P as the ideal generated by G1 through GL by the Hilbert basis theorem, then you know that no, this is not what I want, sorry. It's no, this is not what I want. So I have so U is an open subset here, alright. What I want is the following. I want to show that this U, which is a quasi affine variety, is a finite union of affine varieties. I want to show that, and the way to do that is to realize that the fact that y that U is a so the complement of U inside Y is a closed subset of Y, alright, and it therefore corresponds to an ideal. Okay, so y minus u is z of j bar, where j in A of an is an ideal containing P. Okay, this is what will happen. So you see, I have this quotient map, quotient homomorphism from this to the affine coordinate ring of affine space to the affine coordinate ring of the affine variety Y, and this is just given by mod P. Okay, and what is y minus u? It's a closed subset of y, okay, and y is already a closed subset of AM, so it's a closed subset of AM also. A closed subset of a closed subset is also a closed subset. Therefore, it is given by an ideal in the affine coordinate ring of the big affine space, and in fact, if you want to look at it, it will be given by the zero set. So in fact, maybe I should not put j bar, I should simply put j. Okay, just put j. it will be the 0 set it will be the 0 set of J, and if you consider it as a 0 set in the full affine space, okay, and of course J will be an ideal which will contain P because Zj is contained inside Zp, okay, and now J is generated by finitely many elements, so G1 through GL, okay, and what will happen is and this is of course because any ideal is finitely generated, because this is a Noetherian ring, this is a polynomial ring in m variables, that is a Noetherian ring by Hilbert basis theorem or Emmy-Noether's theorem. So this is finitely generated, so if you take these as generators, then of course if you take the complement of J in the full affine space, that will be a union of the basic open sets given by all these GIs, okay. So you know Am k minus Zj will be union dg I equal to 1 to L, okay, and therefore if you take y minus Zj, so y minus Zj which is u, okay, this will be Am minus Zj intersected with y, okay, and so it will be union I equal to 1 to L dgi intersection y, alright, and therefore but the point I want to make is that each dgi inside Am you know is an affine variety itself, though it is an open subset of Am, it is isomorphic to an irreducible closed subset of a affine space of what dimension 1 more by the Rabinovich trick. So this is, so you know from Am, so you have Am plus 1 k, and you take the 0 set of Gi into some extra variable t minus 1, okay, so t m plus 1 if you want, and you know that there is this there is an isomorphism varieties like this, okay, each dgi basic open set in affine space is itself an affine variety, okay, which means it is isomorphic to an affine variety. What is affine variety? It is the affine variety given by g times gi times a new variable, an extra variable minus 1, 0 set of that in an affine variety of dimension 1 more. We have seen this earlier. So now what I want you to understand is that you know y is a closed subset of Am, therefore y is also a closed subset, y intersection dgi is a closed subset of dgi, okay, y is a closed subset of Am of the affine space, so y intersection dgi is a closed subset of dgi for the induced topology, therefore it will be, and y intersection dgi is also irreducible. That is because of the following fact: dgi intersection y is a non-empty open subset of y, and y is irreducible, therefore dgi intersection y is also irreducible. So the moral of the story is that dgi intersection y is an irreducible closed subset of dgi, and via this isomorphism it will give you an irreducible closed subset of this, and therefore it will become an affine variety. So I am just trying to say why each dgi intersection y is itself isomorphic to an affine variety, okay, and the finite union of all such is your u. So what this argument shows is that any quasi affine variety is a finite union of affine varieties, and if you combine that if you combine that with 1 and 2, okay, you will get that any even a quasi projective variety will also be a finite union of affine varieties. So if you put everything together you will get that any variety is a finite union of affine varieties. Okay, any variety has a finite cover by open subsets, each of which is isomorphic to an affine variety, and thus we say that affine varieties are the building blocks of varieties. Okay. So let me write that down here, that is very important. So thus dgi intersection y is a closed subset of dgi, dgi intersection y is an open subset as long as it is non-empty. It is an open subset, and as long as it is non-empty is irreducible. Thus dgi intersection y is itself an affine variety. Okay, because it is a irreducible closed subset of an affine variety or something that is isomorphic to an affine variety. Thus U is a finite union of open affine finite union of open subsets, each isomorphic to an affine variety. So this is point number, this is observation 3, that any quasi affine variety is a finite union of affine varieties, and then 4 by 2 and 3 any quasi projective variety is a finite union of open subsets. Each isomorphic to an affine variety, and the upshot of all this is the theorem that any variety, whether it is projective or quasi projective or affine or quasi affine, is a finite union of open subsets each isomorphic to an affine variety. So sometimes we say this also in the following way, we say that any variety admits a finite cover by open affine varieties. Okay, that is one way of saying it. The other way of saying it is that affine varieties are the building blocks of all varieties. Okay, so let me write that down. we may rephrase the above as number 1, any variety admits a finite cover by open affine varieties. The other way of saying it is that affine varieties are the building blocks of arbitrary varieties. Okay. So, I mean the importance of this is you will see the importance of this in the following sense. So the first immediate thing is, if you are going to study, if you are going to focus attention in a neighborhood of a point of a variety, then you could as well look at an affine neighborhood of the point and reduce your question to studying a point on an affine variety. That is an advantage. Okay. So let me repeat that: if you have a variety and you want to study in a neighborhood of the point, the variety, then what you do is you choose a neighborhood which is an open set which itself is an affine variety. Okay. The variety you started with may not be affine, it could be projective, it could be quasi projective, okay, it could even be quasi affine. But then if you want to restrict attention to a point, you can find an open neighborhood which is itself isomorphic to an affine variety, and then thereafter it reduces to studying a point on an affine variety. Okay. So the advantage is that if you are trying to restrict attention to a point or a neighborhood of a point on a variety, is just enough to study points on affine varieties. Okay. That is one advantage. The other advantage is rather philosophical. It is that when you it concerns the more general definition of what is called a scheme, which you will see in a second course in algebraic geometry. So the roughly a scheme is something that locally looks, that is locally isomorphic to something which is affine. Okay. So the affines, they build up what is called a scheme. Alright. So you can so roughly speaking, here, you know, if you take an affine variety, you have its coordinate ring, okay, and then from the coordinate ring how can you get back the affine variety? By applying max spec. Okay. So you can say any variety is a is got by topologically, at least as topological space, it is got by gluing max specs. Okay. Alright. If you take a variety which is covered by finitely many affine varieties, okay, then it is the same as saying that you are gluing all these affine varieties together to get that big variety. Okay. But then each affine variety is a max spec of its coordinate ring. So you can say that this big variety is gotten by gluing the maximal spectra of these various affine coordinate rings. Okay. And more generally, the more general thing is what is called a scheme, and that is an object that you get by gluing just not maximal spectra but just prime spectra of rings. Okay. So this is helpful, this will be helpful later when you take a second course in algebraic geometry, but I am saying that the philosophy is already here, that affines are the building blocks. Okay. Alright. So that is a very important thing. Now, you know, there is one fact that I need to prove. I need to tell you that the only regular functions on a projective variety are the constants. Okay. But for that I need to understand what is happening at a point, okay, in a neighborhood of a point, and I also need to keep track of information of what is happening on an open set. Okay. So I have to study regular functions in the neighborhood of a point, and also regular functions on open sets, and the devices that handle these things are respectively called the local ring at a point and the function field or field of meromorphic or rational functions, okay, which is what I am going to introduce next. Okay. So, so what I am going to do next is focusing attention at a point. This focusing attention at a point. So, well, geometrically study functions close to a point and algebraically, commutative algebraically, this is the same as studying local rings. Okay. So, so you know, one important distinction between algebra and analysis is that in analysis you have the limit concept. Okay. So, you have a limit and therefore it helps you, for example, to take a small neighborhood about a point, and you can take smaller and smaller neighborhoods, and using that you can define various things, existence of a limit, and then you can define continuity, differentiability, and you can do analysis. But in algebra a handicap is that you do not have any such notion of limit a priori. So it appears that you cannot do for example study smaller and smaller neighborhoods of a point. So it appears like that, because to study smaller and smaller neighborhoods of a point I need smaller and smaller neighborhoods first, but then the neighborhoods, if they are open neighborhoods, they are Zariski open neighborhoods, and Zariski open sets are, you know, irreducible and dense, so they are huge sets. Okay. So you cannot think of epsilon neighborhoods as you would think of in usual analysis. So it appears that it is not possible to do that kind of analytic study at a point, but the answer is wrong. That is not true. The truth is that you can, even though you do not have small enough neighborhoods, the information is still available. Okay. And that is that comes by studying the so called local rings. Okay. So if you recall, a local ring in commutative algebra is a ring which has a unique maximal ideal. Okay. And so in other words, if you take its maximal spectrum, it is just a singleton. Okay. And every element outside that maximal ideal will be a unit. Okay. And you know, conversely, any ring with an ideal with the property that every element outside that ideal is a unit has to be a local ring with that ideal as a unique maximal ideal. Okay. So these local rings are what we need to study infinitesimal neighborhoods around a point. Okay. And we do it even though we do not have small neighborhoods, Zariski neighborhoods, even though we do not have the notion of limit. Okay. So so let me explain. So what we will do is so the idea is that in algebraic geometry, whenever you want to study something close to a point, you have to always think in terms of local rings. Okay. So what I am going to do now is I am going to define the local ring at a point of a variety. Okay. So the local ring OXP, this is the notation of a point at a point so maybe I will use, okay, at a point P in the variety. Okay. So here of course X is a variety. So we are going to define this, and how does one define it? It's defined in a way in which which extends to defining a local ring of functions of any type. You can use this to define local rings of continuous functions, local rings of differentiable functions, local ring of, if you want, holomorphic functions, and so on and so forth. So the philosophy is very general. So what you do is that so you do the following thing: define OXP tilde to be the set of all pairs u comma f such that u inside x is open, x is a point of u, and f is a regular function on u. Okay, so you look at pairs like this. Okay, so what I am doing is I am just looking at regular functions defined on open neighborhoods containing oh yeah, okay, my point was not small x but it was capital P, so I will change it. Thank you for pointing that out. I have taken my point as capital P, right. So you are just looking at pairs consisting of a regular function defined on an open neighborhood of the point P, alright, and what we will do with this is that we will introduce an equivalence relation. Okay, so define UF equivalent to Vg if there exists W open in U intersection V such that F restricted to W is equal to G restricted to W. Okay, so you put this condition, you define two such pairs to be equivalent if they define the same function in a smaller neighborhood of P. Okay, of course you know this implies that if this is true, this implies that F restricted to U intersection V itself will be equal to G restricted to U intersection V. Okay, this will happen because you know F and G will now be regular function. F restricted to U intersection V and G restricted to U intersection V will be two regular functions on U intersection V, which is a variety. Okay, and if they are equal on a non-empty open set, then they have to be globally equal. I only have to ensure that U intersection V itself is reducible. Okay, and I think that's all right because U intersection V is an open subset of U and U is irreducible and therefore U intersection V is also irreducible. Okay, so these are two regular functions on U intersection V which coincide on an open subset of U intersection V, therefore they coincide everywhere. So well though the equivalence only requires F and G to coincide on a small neighborhood containing, of course I want P to be a point of W, that's very important. Okay, probably I don't even need that. I mean if it shouldn't create any problems. Yeah, probably I don't need this. I don't need this, but anyway I'll add it. Okay. Yeah. So this is an equivalence relation, all right, and now you define OXP to be check this is an equivalence relation. That's very trivial because obviously it is it's obviously reflexive, symmetric, and for transitivity as far as transitivity that's also quite obvious. Okay, so this is certainly an equivalence relation. Maybe I have to think for a moment about if Yeah, so the point that when one thinks with respect to the usual topology one can be misled. One should remember that in the Zariski topology any two non-empty open sets will intersect. That is something that one should not forget. So you cannot imagine a picture where you have three successive open disks, the first and second intersecting, the second and third intersecting, but the first and third not intersecting. That kind of a picture will never happen. Any two open sets will intersect, any two non-empty open sets will intersect in the Zariski topology. Okay, so that is something that you have to remember. So we take OXP to be the set of equivalence classes, which is just OXP tilde modulo is equivalence set of equivalence classes. Okay, and you have this, so you have this natural quotient map OXP tilde to OXP and this is pi p if you want. Okay, and this sends an element u comma f here to its equivalence class, which I will signify by putting a square bracket. This is the map. Okay, now what I want to tell you is that the two things I want to tell you. First thing is that there is a name for these equivalence classes. They are called germs of regular functions. Okay, so equivalence classes are called germs of regular functions at P. Okay, so a germ of a regular function is represented by on some neighborhood of the point is represented by a regular function. Okay, and it is also represented by another regular function on another neighborhood of the point if it is also represented by another regular function on another neighborhood, then these two functions coincide on the intersection. Okay, so in some sense you must think of these equivalence class as defining a particular class of regular functions at that point. So this makes sense as thinking of a class of functions at a point, right? And two distinct classes means that they correspond to regular functions at that point which will not coincide on any neighborhood of the point. Okay, because if you have two regular functions locally defined at the point and if they coincide in some neighborhood of the point, then they will give rise to the same germ. So if you take two distinct germs, they will correspond to regular functions which do not coincide in any neighborhood of that point. That is what it means. Okay, so the moral of the story is that if you want to think of regular functions at a point and you want to distinguish them, this is the way to do it. Okay, so that is the first point. The second point is that this is a local ring. Okay, that is the point. And more importantly, you can do this whole construction not only in algebraic geometry, you can do this in with respect to anything. So for example, you could have started you could be working on a topological space and you could fix a point P on the topological space and you could simply consider pairs where you have a neighborhood of the point and you have a function which is continuous real valued or complex valued function. Okay, and then you could add more conditions, like you could make that function not just continuous, you can make it differentiable if you want, you can make it if it is complex valued you can make it holomorphic or analytic, and you can put the same definition. Okay, and you will see that again you will always land in a local ring. So this definition, this whole process of identifying equivalence classes of functions which agree in a neighborhood of a point automatically produces a local ring. So in a nice way, this is how a local ring, which is completely an algebraic concept, okay, it comes out completely out of geometry. Okay, if you restrict the if you want to restrict the study of functions, good functions at a point, you automatically end up with a local ring. Okay, so if I take my space to be an interval on the real line, closed interval on the real line, and if I take my functions to be real valued continuous functions, then I'll get a local ring which corresponds to germs of real valued continuous functions. Okay, or I could have taken the space to be the plane or some n dimensional Euclidean space, and I could have taken functions f which are defined on neighbourhood of a point and which are C infinity, which means which are infinitely differentiable, okay, and then I will get the local ring of I'll get the local ring of germs of differentiable functions, C infinity functions, and that's what you get when you look at a manifold, okay. And on the other hand, I could also taken x to be a domain in the complex plane or a domain in Cn, n dimensional complex space, okay, and I could have taken f to be I could take the functions to be holomorphic functions, holomorphic in several variables, okay, which is equivalent to saying holomorphic in each variable separately, okay. Then I will end up with again a local ring, namely I will get the local ring of germs of holomorphic functions at that point. So this method of producing local rings is completely geometric, okay. So this algebraic concept of local ring comes out through geometry in this way by restricting by trying to look at functions at a point, okay. Now the fact I want to say is that this is actually a ring. Why this is a ring is because you can define addition and multiplication. In fact, it's not just a ring. In our case, it's actually a K algebra. It's a K algebra, and so let me write out fact OXP is a local local K algebra. This is the fact. So first of all, how do you make it into a ring? How do you define addition, multiplication, and so on? So you define so the operations. So if you give me u comma f, and if I want to add it to v comma g, this is the germ of u comma f, this is the germ of v comma g, okay. Mind you, u and v are neighbourhoods of the point P, therefore u intersection v makes sense, that is also a neighbourhood of the point P. So I will simply define this to be u intersection v and f restricted to u intersection v, which is the same as plus g restricted to u intersection. So this is how I define addition. Then I can define multiplication the same way. I simply restrict and multiply on the intersection. Okay, so you can check that since I am defining these operations on equivalence classes, you can check that they are well defined, okay. So so this is my addition, this is my multiplication, and of course the make this into a ring which is commutative. It is of course a commutative ring because the way the product of functions is commutative, okay. The function defined by f times g is the same as function defined by g times f, okay, because functions are defined, product functions and some functions are defined pointwise, and therefore everything is pointwise being done in the base field, and the base field is of course commutative, and so this makes it into a ring which is a commutative ring with unit element with 0 element. The 0 element is very simple, it is just the class of x comma 0. So you have the constant functions are always there, so you take the function 0 on the whole of x, that is a regular function, and you take its germ, that is the 0 element, and unit element is given by x comma 1, you take the constant function 1. Constant functions are of course regular functions always, so that is the reason why the constants k, the field base field, sits in as constant functions in the ring of regular functions on any open set. So if you take U any open set, then OU is of course a k algebra because k sits inside OU as constant functions. Okay, so this makes it into a commutative ring with this as 0 element and this as unit element, and further it is a local ring. Why? Because the subset MP M of P, so let me write MXP to be the set of all germs U comma F such that F vanishes at P. Okay, so whenever you take a germ, it is defined, it is represented by a regular function on a neighborhood, and you take all those, take the subset which corresponds to functions which vanish at that point. Okay, then this is a maximal, this is an ideal in OXP, that is very clear, because if a function vanishes at a point, then a function multiplied by any other function will also vanish at that point, and sum of two functions vanishing at a point will also vanish at a point, so it is an ideal. Alright, and every element which is outside that, you take a function, you take a germ which corresponds to a function, it does not vanish at a point, it will have a it will have an inverse, because the moment f does not vanish at P, then by continuity f will not vanish in a neighborhood of P. Okay, on that neighborhood 1 by f will be a regular function, and f into 1 by f will be 1 on that neighborhood. Therefore every element outside this ideal is going to be unit, and that will tell you that this has to be the unique maximal ideal for that local ring, and that ring will be local with this unique maximal ideal. So let me write that any element outside MXP is of the form P comma G with G of P not equal to 0. Since G is continuous, G does not vanish, in an open neighborhood W of P, and clearly 1 by G belongs to OW with W 1 by G germ of this into V comma G is equal to x comma 1. So every element outside MXP is a unit in, that is an invertible element in this ring, which implies that OXP is a local ring with unique maximal ideal. MXP. Okay, so this is a local ring at a point of a variety. Okay, and so immediately there are a couple of facts about this. So the questions that you will ask is, we have defined this local ring just using regular functions in a very abstract way, can you really write it down commutative algebraically? And the answer is yes, you can write it down if you are looking at a point on an affine variety. Okay, you can write it down as the localization of the affine coordinate ring at the maximal ideal that corresponds to that point, okay. And that is one fact. The other fact is that the local ring will not change if instead of X you take an open subset which contains the point P inside X. So instead of computing the local ring of X at P, if I compute the local ring of U at P, where U is an open subset of X which contains the point P, I will still get the same local ring, which means that the local ring depends only on the neighbourhood of P, on a neighbourhood of P. It does not depend on the ambient variety, okay. So the moral of the story is that if you want to really work with the local ring at a point of a variety, you know already that that point can be surrounded by an affine open, because I have told you that any variety can be covered by finitely many affine opens, and therefore the local ring of the variety at that point is the same as the local ring of the open affine subvariety at that point. But then when you look at the local ring of an affine variety at a point, there is a precise commutative algebraic expression, namely it is the localization of the affine coordinate ring at the maximal ideal corresponding to that point. So all this helps us to reduce study of local properties to study of local rings of affine coordinate rings, okay. So that is the importance. So with that I will stop now.